All right, cool. So thanks everyone for joining the June Auckland Rust meetup. After last month learning about high performance things that Sigma Prime was sharing, it was really interesting, and the game dev ideas that Azrael was sharing. So this week we will have awesome and creative new topics. And I think that something that I've heard both in Centrality and in other community conversations is that a lot of the people that start developing in Rust come from the C++ background. So I think it's really cool that Alex basically volunteered to share the experience of the transition, because probably a lot of other people are also going through the transition, and if not, then a lot of the OG Rust people here can at least like understand what's it like to transition from C++. So it would be really cool to understand what's that journey looking like, and see how we can hopefully support more people to start developing with Rust. And then Joseph afterwards will share with us some real-time collaborative editing. So that would be interesting to see what you have there with Statecraft, was it?
Yeah, that's right. Yeah.
Cool. Cool. So without further ado, Alex, would you like to hijack the screen share?
Yes, thank you. I'm gonna share my screen. Oh, you cannot start. You need to first.
I need to stop, yeah?
Yes.
Got it.
And now I'm gonna share mine.
Excellent.
Okay, maybe I can. So hi everyone. I am Alex Sedighi. I am a senior developer with Centrality, and I'm so happy to be here tonight and share my experience with Rust. Still need to see myself as well. So I'm, as Daniel mentioned, I'm coming from a C++ background. And when you have a background, especially a long-term experience with another language, you've already got some structure or in your brain that you want to put stuff on and link on that structure and link with the concepts that you have already learned. And that's actually good because it can streamline your learning process, but at the same time, it's got its own disadvantages. For example, there are things that when you are studying Rust, you quickly get that this is something I haven't learned about before, and I need to know. For example, this lifetime annotations. But there are other things that when you look at them, you think, I think I know. For example, I know the definition of a reference. I have worked with references in C++, and here we are talking about references in Rust as well, and they look a little bit like the other one. So you may not get to the bottom of the concept, and then you later struggle with what it is. a little bit disclaimer that my presentation might appeal more to those who've just started, might appeal more to those who've just started learning Rust. But I hope it would have some other, like maybe some nice things for others as well. Yeah, that's my intention. I just wanted to see, to show to the other C++ developers who are joining, there are some road bumps that they need to be aware of, and there would be mistakes that we make, and it's common between us. These are the topics that I would like to cover tonight. This is actually my initial list. But then when I try to make all the slides, I realized that we probably wouldn't have time to cover this one, macros. Macro was actually one of the topics that has got a lot of tears for me. So it's a story with a lot of tears. And I would really like to share my own experiences and like my own complaints with the community. But I think we would need it for another meetup session and another night. But hopefully I try to cover all the other topics that you see here. So let's start with basic stuff. Anyone who's worked with Rust knows there is cargo, which is really cool. And we didn't have it. We would have like other third-party tools that would do similar stuff in C++, but cargo as an offering from the language is really cool. And everyone who's started would know a few commands right away, like new, build, cargo new, cargo build, cargo clean, cargo test. These are very basic and everyone would know about that. But there are, and once you know those basic concepts, and you can do almost everything that you want, and it might cause that you don't go and learn more about cargo. And there are things that you would later realize, these things has been really useful and I could use that a lot. One of them is cargo check. So if you like to compile a package, but you don't want to waste time with the final step of actually linking and generating the binary, which in many projects, it might be the step that would take longer somehow. This cargo check would help you a lot, especially if you are working with a very big code base, like the one that we have in Centrality and like parity companies. So they have created a really large code base, and this takes a lot of time to build, and that's really a pain. So that would be useful to know. If you don't know, now you know. The other thing is cargo update and cargo fetch. Again, there's a concept cargo lock. Cargo lock, what it does is locking everything that all the dependent libraries, everything that your project needed to make a binary, it would make a record of those and keep it with the binary. So every time you make a change, it wouldn't necessarily go and fetch like the latest releases of the libraries that you have used, but sometimes you need it, especially if you've got more than one project, and one project is you base them on like GitHub, and you update one of the projects, and the other project is dependent on the first project. So you update the first project and you want to use it in the second project, and you make it, and you see it's happening. It's not working, and it's like you may probably waste a little bit of time, as I have done, to realize that, oh my God, that's actually the project. Even though I am building it again, it's not gonna get the latest dependent libraries because it's locked. So there are things that you can do to work around this. So you should know one of the things that you better not do if you are dealing with big projects, and that's rebuilding, cleaning and rebuilding. That can help, but that would take a lot of time, and it would waste a lot of time if you are having a very large project. Instead, you can use cargo update, which updates, so based on what you have said in cargo 2ML, it would know the rules for which libraries and what versions are allowed to be used, and it would go for those that you have said, I would need the latest version, would update that this is actually the latest version, but it wouldn't bring the changes until you do cargo fetch. So that this mix of cargo update, cargo fetch was useful for me, and I wanted to share with you. But remember, when you do cargo update, the log file is updated. So it has brought some, the newest, for example, of some of the stuffs if you have asked it to do. And if you are not really compliant with the newest versions, it might break things as well. The other cool things that I hadn't done until recently was using this cargo doc -- open. You wouldn't believe even a simple hello word that you create with Rust. You can try this cargo doc -- open and see how amazing it is, and what a nice view of your documents, and not only the documents that you have added to your project. If you have used a library, those libraries is also, document for those libraries is also fetched, and it's built locally, and you've got it locally, and you can open it. It will open it for you, and you can browse it. This was really useful, but for the sake of time, I would try to skip faster and don't spend much time on this. The other thing are about what are the default assumptions of the Rust compiler. They are based on, what I have learned is, they are based on the best practices. We really liked and encouraged everyone for those best practices. But we couldn't enforce it in C++ without using third-party tools. But Rust is actually has made some really smart decisions about what should be the assumption of the compiler. So examples, variables. Whenever you create, you define a variable and you bind it to something, as it's the terminology in Rust. In C++, you might say assign something to it. So variables are by default immutable. They are by default const. Any definition that you create is by default private in Rust. Though I have put this star to say private is one of the things that you need to learn what is the meaning of private, but because you think you know private, got an understanding of private in C++, and it's a bit again different in Rust. Any assignments that you have by default imply move unless the type that you are assigning something to it, the type of the variable that you are assigning something to it, or if you've got a variable and passing it to a function, if that type has got the copy semantics, then the assignment would be copied. And it would be definitely copied. It's got the copy semantics. It's not like it would choose to move. The other thing is, any reference that you create in Rust has got a lifetime associated with it. So for any topic, I try to have some examples, and I put all these examples together in a project, in an open source project that I have shared on GitHub, and you can later browse and see if it's useful for you. My own approach for these examples was to be, I wanted to create very minimalistic examples. I don't want anyone, including myself, these examples was primarily they were myself, and I didn't want to spend time to think, let's decide about a project to stop. I want the simplest thing that in abstract would tell me how something works in Rust. So now we are talking about references, for example, and what I said is any reference that you create has got some lifetime associated with it. So this test is the test of lifetime. For example, here I have introduced a variable. I haven't yet, what is the type? But the scope is outside this. Inside, I have an x, which is of type integer. Then I return the reference of that variable and keep it in R. So now Ross knows that R is actually a reference to me. And then I check if I do reference, and here it is, one of the differences of Rust with C++, that you do reference a reference similar to C++ pointers. So reference is not quite reference as we know. So you dereference it, and I have checked if it's actually showing fine. But if I had done this here, this reference to X has got a lifetime. The lifetime of this reference is this scope. If I would try to use R here, it's out, the reference is not alive, and you get failure, compile failure. So that's very normal. Everyone who knows the basic would know about this behavior of reference. But one of the things that was a little bit more interesting to me was I did the same thing with string literal. Got, again, Z here, X and Y to constant string literals. And then I have used this longest function, which was an example in Rust. The longest would check between two string literals, which one has got a which one is longer, and returns the reference to that one. So longest returns a reference, and the variables are introduced inside this scope. I check the reference, and here I do the same thing that I couldn't do here, and it works. And there's no problem. How come? A reference is outliving a value that is x. You think the x is not alive, but the reference is still alive? The answer is, for example, here, the string literals all have the type ampersand static, which means they are they have a static lifetime. They are always there, so you can do that. The Z is still okay to check. Again, the other thing is about like lifetime annotations here. If you would try, for example, you've got two different references with different lifetimes. They can be different lifetimes. And you've got two lifetime generic parameters, and this is the return. And if you would do this instead of saying that all three has got the same lifetime, you get compiler error. And it was interesting again to me because when you check the error, it will tell you, hey, I don't know, you may return X or Y. So the lifetime of the reference might be related to either X or Y. You cannot choose the lifetime of X for the return value, which was nice and very straightforward, this one. The other thing, back to the assumptions of the Rust compiler, any code that you have is safe unless otherwise specified. And there's a particular meaning for this safe, but we don't have time to probably dive in. A little bit more about references and the differences that they have. So as I mentioned, dereferences to star, like C++ pointers. And here in Rust, even literals and R values can be referenced, which means they are more similar to C++ const reference, but they're not const here. You can actually get a reference of an R value or a literal and then try to change it and work. It works in Rust. Because when you create an R value, it is, or literal, there is like an anonymous variable or a memory for that by compiler, so it knows how to reference it. When you try to access member variables and methods of a reference, you use dot. So from this aspect, is similar to reference in C++. But when you pass, or if your function, for example, has got reference input, reference input parameters, you cannot pass a value directly as it is in C, as it is in C++, sorry. You should always take their address and pass it. So they are not exactly the same thing. And here we've got and MUT or mute, I don't know, and mot, how it is pronounced, because I have always read it instead of hear it. And it's normal reference You cannot change the value of the address memory. You should use this. And a single deref, when you dereference, may trigger a chain of derefs. And this is a concept called deref coercion. And when you look a little bit deeper, you would see that reference, which is like entity here, is more like shared reference. And ambmute should be called unique. The reason is, even though the normal reference is just cannot change things, but there are situations that you use a normal reference and change it. And the very important thing about ambmute reference is that you cannot have any other reference at the same time. You've got a mute. I also, like all the other topics, have got examples of how references and deref coercion, for example, works. And I would suggest, if you're interested, look at the example yourself and see if that makes sense to you. But one interesting thing that I would want to say is, as I said, any type that you create is by default a move. When you use it in an assignment or you pass it into a function, it would be moved, unless you say that it's, for example, deriving from copy. If you say this type is deriving from copy, then it would always copy. And for primitives like iSize, which is integer, they are copied, so they would always copy. And that makes it a little bit, for a C++ trained eye, that makes it weird, because you see the assignment and you don't understand why it is somehow sometimes working as copy and sometimes working as move. And it goes back to the type. And the other important, if for example, in this structure, if the X wasn't a primitive type and it didn't have the copy semantic, then you couldn't like do p.x equals something, assign p.x to another variable, because it says you are moving part of a movable type. You cannot move part of something. And that's something that if you see it works, you would know that this is copying, not moving. If you don't want the decision to be made for you, or copy, to be always the same, you can use clone, which says whenever I assign it, it is moving. If I want to copy, I would clone it and move the clone. So it always moves, but when you need to copy it, you've got the clone function. Back to the presentation. Another interesting topic is const in C++ is like, what is the relationship between const and immutable? So we had C++ const expression, const xpr in C++. Here, it is called const in Rust. If you see const function, it means const fn in Rust, it means const expression. It's equivalent to const expression in C++. The normal const here is actually the default. If you don't see anything, it's const. The equivalence of C++ const method is, again, any function that is having this and self instead of and mute self, and mut self. This means that that function is const. And this is the equivalent of normal function, C++. So that's something you think this is the normal function, but in terms of C++, this is the normal function without const. This is const function, the first one. So the last one is interesting. You know that in C++ we had mutable for a variable, and it would be very useful for at least in two many popular scenarios, you would need mutable. One was when you had a class and wanted to add like a mutex kind of lock. So that class and that function could be const, but locking needs to be mutable, but you don't want to like make everything not const, for the sake of just a lock. So you make that lock only mutable. Here in Rust, we've got this mutable, but it's a little bit different, and it's called interior mutability. That's the term that would get you to the answer, and it's true ref cell. And I've already got an example of how it works. Maybe in the project that I told you. Interior mutability. There's an example of a mocker, which is the second scenario that mutable could be very useful for. Because in mocker, sometimes you want to mock a function that is const, and but you're mocking. You're not actually implementing that function, and you need to do stuff. You need to make changes somewhere for the mocker. So you want to present yourself as const, but internally not const. And that's when you need ref cell. But I again leave it to you to explore if you are interested. Briefly, ref cell would help you to borrow a mutable or a normal reference at runtime. And borrowing rules still apply, and typical uses lock and mock. This is another thing that we are not familiar with, and that's shadowing. Again, we've got shadowing in C++. When you have a variable defined in an outer scope, and then you've got a variable inside another scope, defined with the same name, the inner one is shadowing the outer one. But in Rust, in the same scope, you can define variables, or as they say, bind several variables with the same name. And as soon as you define another variable with the same name, the second one is shadowing the first one. And it's weird, again, to a trained, to a C++ trained eye, it's like weird that you can define a variable in the same scope with the same name. And it can be really a bad thing. I would say why it can be a bad thing. But what was the good thing that they allowed? They, the Rust has got two important splits. This is big. Correctness is very important in Rust. At the same time, brevity is very, very important in Rust. And they didn't want to introduce a lot of boilerplate. So I guess this is coming from the second split of the Rust. And so they wanted to, you've got, for example, in this case, you've got a variable foo, you want to unwrap it. So you have wrapped it, for example, in an option. So this is the returning, whatever it is, it's the same thing. So you don't want to create, you may not want to create another name for the same thing, even though the type is different, especially that you know that once you unwrap this variable, you don't want to use it anymore. So you may say, okay, this is foo, but you've got the little word here, let, that would say, this is not the same foo, this is a new foo. It's from the type wise. This is a different type of foo that's actually unwrapped version of foo. Or this is one of the cases that they say, yeah, that's probably a good use. The other thing is like decoding something. Again, you've got a number, and this number is, for example, in string format. You parse it, unwrap it. So the number is still the same number, but the format, the type of the number is now integer. And you don't need the previous one. So you use the same name and shadow it. So the same, it still looks cool. But when it can go wrong? And why is it potentially a bad thing, especially in the hands of those who would not would be cruel to next developers, to those who would want to maintain a code. And that's the reason for that is there's no enforcement actually from Rust that a shadow should be irrelevant at all. So you can use the same name for two irrelevant things. But once you can do, there's always be someone who would do it for irrelevant things. And the other thing is, it can make, in some cases, the code hard to read. Because sometimes you miss to see this little let among hundreds of lines of code, and you get like confused how something happened, and then like after a while you realize, oh my god, this is a different variable. It has a different change because there was a let for that variable name in a line. So anyway, maybe briefly I said that the reason you see a lot of mice figure in my presentation is a fun fact that I recently learned, that after COVID-19, there has been an influx of mice in people's houses. And I was like, what's the correlation of COVID-19 and the mice everywhere? So, and I realized that's because they don't get enough food that they would get otherwise once like all the businesses were working and restaurants were open, cafes, so they had a lot of food waste. But now they are hungry and looking for food. They are everywhere, including in my slide. So moving on to the next topic, and I am already like getting very close to the time that my time, and I have a lot of other things to share with you. So I try to actually present a little bit faster. The other nice thing about Rust, it's nice, but it's weird, again, to C++ developers, and that's, you can very well see in the example here. Rust can see things like type definitions, infer them from what you have done in the lines further after you have used it. This use, for example, this particular example, everything is arranged in the worst possible way, but it gets compiled. Here, you've got function, an introduction of a function init A. There is an A of type A, and there's no type A. You say, where's this type A coming? Oh, this type A is introduced later and here. And it doesn't matter. In C++, it would matter. This should be coming first. Again, this function is introduced later. Doesn't matter. We are implementing a trait or structure that we haven't yet introduced. We are like, use does the same thing as include or something similar, not as, but something similar as include to C++. And you think, include should be up. No, it can be the very last line and it all works. So that's nice. Again, if you would want to know is use is like include, you would realize that use is later. It's super picky. In C++, if you include something and, for example, a definition of type A, and that type A itself is depending on type B. Once you pull type A, you have pulled type B as well, but it's not the same in Rust. It's like, so one of the things that would probably waste a little bit of time for you is somehow coming across the errors that you get from like pulling in a type by using use, but not pulling the trait that this type is implementing, and you actually need that trait. And you're just, how? This is implementing that, but it's not working like that. You need to individually use the trait as well. And another example is if, like, you've got a structure A, and the structure A has got member variables, and member variable is of type B. You think just by using A, you have brought the type B, but it's not the case. If you need to use A in a way that you are accessing its member, then you need, and you should actually individually bring the type B. So again, I have examples there. This is another one that's cool. That was cool for me. And that's a question for you. How many type definitions you see in these lines? Can anyone answer that? So we've got one structure, one type definition, S. Another structure, which is generic. This one was also generic. Yeah, so 2 so far. This structure D is tuple struct. So it's got a member without name. So it's a tuple struct. And that member is of type S. Okay, so far still we've got just 2 types. One is tuple struct, one is the normal struct. And S would get like a generic parameter. And when you look at the generic parameter that we are passing, you see two parentheses. And these two parentheses is making another, the third type. So we are actually introducing three types. And that's why you think I would be like first confused why S has got just two generic parameters. How could I actually pass two generic parameters to S? But we are not passing these two generic parameters together is making one type, the third type. Moving on, when we say private in Rust and we say everything is private, it's not quite the same again as C++. That was one of the things that was confusing. You see, you introduce structure and they say all the structure members and the structure itself is by default private. And a few lines later, in the same scope, you have access to the member of the struct. But when you read carefully, you realize that every object, every type in Rust makes these different relationships with other types and other parts of the code. And either they are from the same scope or from the parent scope, the outer scope, or the child scope, or the sister scope. And interestingly, privacy, when you say things are private, it means private to the parent, either parent or sisters, or completely irrelevant scopes. Not the same scope and not the child scope even. The other thing that you would really need to, I would really suggest for those who started to learn very well, is the fully qualified syntax. That's really necessary because you can any trait introduce functions and methods. Then traits can even introduce default implementation for a function or a method. Then you've got the structs when you can implement their own functions, and then structs may implement traits as well. What if a name is used in both places? Now you need to resolve the situation, and the situation would be resolved in using fully qualifier. Fully qualified syntax. And you would need really to do this stuff, especially more in generic code. And you get across generic code more in Rust than any other language that I have learned so far. And this is an extreme one that I have come across this example of balance of. So this is an extreme one that was like, oh my God. Whenever I come across a thing like this, I would say, probably someone has made a stupid decision somewhere that we ended up needing this, but I might be wrong. But when you only need to learn this fully qualified syntax well to be able to understand what is happening in this one. The other interesting thing about generics is this Tuplefish, and that's the last thing that I want to share with you. Again, in C++, when you introduce a generic parameter, you use this angle brackets, and when you specify the type for a generic parameter in an expression, you again use the same angle bracket. But in Rust, if you are specifying a type in an expression is different than a statement or a type definition. So for example, vector here, this is a type, you are introducing a type, vector of U8. So this is the normal. Here, you are specifying the type of a generic in an expression, which is evaluatable. You can, what is the terms of expression? The meaning of expression, we need to get back to that. Then you need to use a thing that is similar to this symbol, and it's called turbofish. And there are more examples of that. Again, here, this is turbofish is used. Interestingly, this is an expression. Inside this expression, you needed to use turbofish, for example, and you pass the type. Now you are passing a type. This part is a type. Vector of I32 is a type, so you don't use the turbofish inside because it's type, it's not an expression. And I've got some more examples for you here. I hope you have enjoyed my presentation, and thank you for listening. And any questions you can ask either now